Hey everybody. So we've been discussing what is essentially undamped oscillations, like a mass on a spring where the surface is smooth and there's no air resistance or anything. So this would bounce back and forth forever, right? Or like a pendulum where you have a mass and a length, and this would swing back and forth with no air resistance forever. Not really what we experience in life. So let's purposely introduce some sort of damping to the motion. For example, imagine you took a cylinder and just fill it with water or oil, let's say oil, and you put a piston over here like this. And you drill a bunch of holes in the piston. Okay, now what would happen if you push down here slowly? Then there would be some force opposing your motion. And then if you try and push faster, what would happen, right? The faster you try and push, the more force would oppose you. So this damping force is proportional to the velocity, but in the opposite direction, right? The damping force is proportional to the velocity, but opposing your motion, right? The faster you push, the more damping force there is, opposing your motion. And, right, imagine this is a plate over here and a plate over here. You put a spring over here, and this is like car suspension. There's a spring and a shock absorber, which is a damper. Sometimes the spring is coiled over the damper. Okay, so let's introduce this. Let's turn this horizontally so that it's a non-homogeneous. So it's a homogeneous ODE spring. And then you can represent a damper just kind of like this. So this represents a damper that's kind of like this. And there's some coefficient associated B, and then some string constant K. And let's say this is smooth still. Okay, so now the free body diagram looks like if we're on this side and let's say it's moving toward the right, then there would be spring force, damping force, normal force, weight. So this is the damping force, spring force. Okay, so then some forces in X, we got minus, right? It's in the negative X direction. That damping force, the spring force is also in the negative direction. And that's it, mass times acceleration. Let me move all of this on one side of the equation. Okay, and let me just divide everything by mass. There we go. And acceleration is the second derivative of position. Velocity is the first derivative of position. And here we go. We have a homogeneous second order ODE. The difference though now, before we introduce a damper, this was simple harmonic motion because the acceleration was proportional to the displacement. But now it's not. So thanks to the damper, this is no longer simple harmonic motion. The answer isn't just some sort of sinusoid. This was true with no damping. With damping, like if you try and substitute this here, it's no longer, right? Like the time derivative of this would be sine. So this is cosine, this is sine, second derivative of cosine. That's not okay. This doesn't work. So I will tell you the answer and I'll leave the proof to another video that is optional viewing. You can ask me about it. It'll take maybe half an hour to explain. So I'll just tell you the answer. So the answer depends on the values for the spring. So let's say, let me make up some values. So let's say it's 1 kilogram. Let's try and make simple numbers. Okay, and then that coefficient B is 3. K, 16. Okay, let's stick with this for now. All right. And then if we had some initial conditions, like the initial position is something, and the initial velocity is, I'll just make up some number. Okay. And the solution depends on the relationship between these values. So if, let me do some substitutions already. So I'll call this D. B over 2m. And omega naught is square root of k over m. So these have to go together. So I'll include it here. Okay, so include these. This is some kind of damping coefficient. And this is the undamped natural frequency. If you recall, when we had no damping, remember that it was like this? That's this, undamped natural frequency. And everything depends on the ratio between, the relationship between these two. So for example, case number 1, if that damping coefficient is less than the undamped natural frequency, so this is scenario number 1, this is called underdamped. And the answer looks like this. Some coefficient e to the minus dt. D is this, right? Cosine. Okay, now this is yet a different coefficient. So this is the damped natural frequency, which looks like this. Okay, so this is the answer. If D is less than omega naught. This is underdamped, and this is the answer. Now, if D equals omega, this case is called critically damped. And the answer, the position looks like, I'll pick a different coefficient, a different letter. There you go. Okay, so there, again, these are unknown coefficients that you would need to solve for these using the initial conditions. Right, this one has 2. Notice that there's a t over here. Okay, now third case, if D is greater than omega, that's called overdamped. I'll explain why we call it that in a second. So the solution for the position would look like, okay, I'm going to have to introduce yet another new variable, which I'll write down in a second. For D is, take a look, it looks like this, but the other way, oh, sorry, wrong letter, H. It looks similar to this, but the other way around. Okay, so then there. These are the 3 different cases. So it all depends on the numbers, what the numbers are. Okay, so 3 possibilities. And it's called this because if I were to graph, or let me make one picture here. If we graph the position of that mass as a function of time, if it's undamped, it's some sinusoid like this, right? But when you introduce damping, where it's underdamped, it looks like this. So this would be underdamped. So it looks like a sinusoid, but it's kind of decaying. So that's underdamped. Overdamped looks more like exponential decay. I can draw it so nice. Exponential decay. See how it's an exponential function that's decaying? And then critically damped is kind of still exponential decay, but faster. So the blue one is critically damped. The red one I drew is overdamped, and then the black line was underdamped. Okay, so you don't have to memorize it or even know where it comes from. These are the answers. You can just use these. Okay, so now let's try it with some numbers. So I made up these values here, right? So is this underdamped, overdamped, or critically damped? Okay, so let me move this where I have more space. Okay, actually I'm going to change this to a more even number. Okay, so let's say these are the values given. Now, what is the undamped natural frequency? Square root of k over m. So 16 over 1 square root would be 4. Okay, how about this one? B over 2m. 4 over 2 times 1, so 2. Okay, so see, d is less than omega naught, so this would be underdamped. So this is the answer right here. Okay, and then how do you get, so for the unknown coefficients, let's do that right now. Okay, so here's the answer. And we already know d, that's 2. And omega d, this would be, let's see, 4 squared minus 2 squared. Okay, so we got omega d, so we got this. We got this. Now we just need to find this amplitude and this phase angle, and then we're done. So how do we get that? You would need to use the initial conditions. Right, so then initial condition here, the initial position is 0.1. So x at t equal to 0 would be a e to the 0. That's 1. Can I just not write it? I'll just leave it there. Okay, e to the 0. Cosine of, this would be 0. So just cosine of phi. And that's it. Okay, can I erase e to the 0? Okay, there we go. And that is 0.1. Okay, so we got this. Oh, let me just, we got this right here. Now let's use the other initial condition, the initial velocity. We can't quite use it. We would need to know the velocity first. So what's the velocity? Let's take a derivative of this. The velocity, just take a derivative. Okay, so this is a product, so we better use the product rule. So the derivative of this is minus d e to the minus dt, and then leave this alone, plus leave this alone, and then the derivative of this, which would be minus, and then sine, and then don't forget the chain rule with this omega. Okay, there we go. All right, so this is the velocity. At t equal to 0, the initial condition, right? So this would be minus a d e to the 0. So can I just leave that as 1? Cosine of, this would be 0, so just cosine of phi. And let's see, what do we have here? this would be e to the 0. So minus omega d a e to the 0 times sine of 0 plus v. So like this, right? And that would be this number minus 0.2. I didn't write units, sorry. Okay. All right, so now we have these two equations to solve for these two unknowns. Okay, so to just do substitution. However, let's say, which way should we go? How about a is 0.1 over cosine, and then substitute that over here. So then you have minus, let's see, minus d 0.1, let me call it minus 0.1d, cosine over cosine, then minus omega d, and then this would be 0.1 sine over cosine. I'll just call it tangent. Okay, so now take a look. Again, d, we know the answer, it was 2. D is 2. I'll just put that value in right there already. Okay, so then there's only one unknown, right? Just move this on that side and then solve for omega, solve for the angle, the phase angle. Once you get that phase angle, plug that number right here and solve for the amplitude. Okay, now let's just, for practice, let's change up the numbers a little bit. Okay, let's say I make this something, let's turn this into 8. 8. Okay, so new problem. This is 8. So then d would be 8 over 2, which is 4. So now look, omega equals d, so this would be critically damped, right? So it would be this. Okay, so let's try this one for practice. Okay, so this is critically damped because these are the same. So I grabbed the answer for critically damped, which we have to figure out these two unknown coefficients. Right, we already know d is 4. So how do you do that? Use the initial conditions. X at t equal to 0, that would be 1 e to the 0 plus b2 times 0. Okay, so then that's it. 0.1. Okay, so actually we're done with b1, so we got this already, that's 0.1. So how do we get the other coefficient? Use the other initial condition. So we need the velocity. So take a derivative, minus d b1 e to the minus dt. Take this derivative. Oh, notice it's a product rule, so I'll take the derivative of this, which is 1, plus, I'll leave this alone, and then take the derivative of this, which would be minus d e to the minus dt. Okay, so this is the velocity. Now, the velocity at t equal to 0, minus d b1 e to the 0, plus b2 e to the 0, plus, that's 0, so this is 0, equals right here. Okay, so we already know b1. Take that answer, plug it in right here, solve for b2. Okay, so now let's try another example. Let's change this to something more like 10. So if this is 10, then this would be 5. And now if we look at this, d is larger than omega naught, so this would be overdamped. So let me grab that solution and let's try this one. Okay, so this is the solution if it's overdamped. So then we know d and we know omega, right? So h would be square root of 5 squared minus 4 squared. Okay, which in this particular example will just be 3. Okay, so we know h, we know d is 5. So, right, it's c1 e to the minus d plus h, so this is negative 2. c1 e to the minus d minus h, so this is minus 8. Okay, but we need to figure out these two unknown coefficients. So how do you do that? Use the initial conditions. X at t equal to 0 would be c1 e to the 0, okay, plus c2, oh, there should be a 2, sorry, c2 e to the 0, okay, equals 0.1. Now, let's use the other initial condition, but we need the velocity. So let's take a derivative of this. So that would be minus 2 c1 e to the minus 2t plus minus 8 c2 e to the minus 8t equals negative 0.2, which is just the number over here. Okay, so we got v, sorry, not yet. Here, v at t equal to 0 is minus 2 c1 e to the 0 minus 8 c2 e to the 0, which is, now we can use this number over here. Okay, so look, you have two equations, two unknowns. Just do substitution, right? Like c1 is 0.1 minus c2, take that, plug it in right there, and then solve for c2, get that answer, plug it in right here, and then you have c1. Then you have both. Okay, so let me go back here. This should have been a 2 right here. Okay, so maybe I'll take a screenshot of this and I'll just post it as a separate image so you just have it separately. Okay, so give these a try. It's all about, I'll walk you through again. You just figure out whether it's underdamped, overdamped, or critically damped based on these two values. So you just calculate the number, and then based on the numbers, you know which of these three solutions to use. And then it's just a matter of solving for these two unknown coefficients, or these two unknown coefficients, or these two. Okay, so let me know if you have questions, and I'll see you in the next video.